Hello everyone, this is part 2 video on past year NEET questions from the chapter D&F Block Elements. Now those who are looking at this video can probably take a look at the first part also so that you will have continuity. We will start with a question that has come in the NEET paper 1 of 2016. It's a straight question based on the electronic configuration. The electronic configuration of EU atomic number 63, GD atomic number 64, TB atomic number 65. So it's a straight question. We have to tell what is the electronic configuration. What is this EU? EU is symbol for what? It is symbol for europium, atomic number 63, and GD is symbol for gadolinium. TB is the symbol for terbium. So 63, 64, 65. Now generally if you look at the electronic configuration of the lanthanoids, all of them are what? Lanthanoids. So what is the lanthanum electronic configuration? Xenon 5d1 6s2. Then the electrons will start entering into the 4f subshell. So cerium, it starts from cerium 4f1. The 5d1 will be as it is. Now if you look at the other electronic configurations, right, the 5d1 electron is being shifted to the 4f subshell itself. See, praseodymium, right, it is not having xenon 4f2 5d1 6s2. Instead, what is it having? What is the arrangement for praseodymium? Praseodymium is what? Pr, right? What is the arrangement for this? 4f3 6s2. So this adjustment is because of the 4f and 5d, they will be having energy difference, of course, and the stability factors are the one that will decide where this electron will be placed. Like if you look at gadolinium, we still have the electron in the 5d. Similarly, lutetium also we still have the electron in the 5d, because of course here 4f is completely filled. So if you look at the electronic arrangement of the lanthanoids, the starting from, because the lanthanum is not part of it, cerium, gadolinium and lutetium, these are the only elements where we have electron in the 5d. Otherwise that electron is being shifted to what? 4f itself. So if you look at the electronic arrangement, right, we can also remember this with the help of a mnemonic. So the general mnemonic that people use is Segal. Okay, so C is what? Cerium, Ga represents gadolinium, and L represents what? Lutetium. Because lanthanum is not of course counted, that's not a part of the lanthanoids, are the ones that will start after lanthanum. Okay, so this is not a 4f element. 4f elements will start from here, cerium. Now they are asking a straight question. So other than the cerium, gadolinium and lutetium, right, none of them will be having the electron in the 5d. That electron will be shifted back to the 4f itself. So if you check the arrangement, right, they are giving us the atomic number. So we remember the lanthanum atomic number. So atomic number of lanthanum is what? 57. So from there we will start counting. See, what is the lanthanum? What is the lanthanum arrangement? Xenon 5d1 6s2. From then we will start entering. So europium is what? 63. Means we are adding how many electrons? 6 electrons we are adding. So europium is not going to have electron in the 5d, right? Means we are adding 6 electrons plus the d electron also will be shifted to the f. So let's look at the europium arrangement. It is what? Xenon 4f7 6s2. Then gadolinium, here this is the arrangement where there will be the 5d electron retained. So it will be what? Xenon 4f7 5d1 6s2. So if you look at these options, right, europium, what is it? 4f7 6s2. Gadolinium 4f7 5d1 6s2. Then terbium. So terbium is what? So here the electron, the f electron will be shifted back to 5d. So from here if you just increase one step, means 4f8 5d1 6s2 should come, but we are not going to have the electron in the d level, right? So it will come back to f, means what? 4f9 6s2. So what is the terbium arrangement? 4f9 6s2. So the correct option is europium xenon 4f7 6s2, gadolinium xenon 4f7 5d1 6s2, and terbium xenon 4f9 6s2. So here the only thing is, what are these elements which will have the 5d electron? What are these elements? Cerium, gadolinium, and then lutetium. You can remember the mnemonic Segal: cerium, gadolinium, and then lutetium. Only these elements will have the 5d1 electron. Other cases, the d electron also will be shifted to the 4f level itself. Let's go to the next question. This is a question that has come again based on the electronic configuration. This has come in the year 2015. Gadolinium belongs to 4f series. In fact, previously only we were discussing about it. Its atomic number is 64. Which of the following is the correct electronic configuration of gadolinium? So the way we were analyzing it, right? See, what is it for the lanthanum? Lanthanum atomic number is 57. What is the arrangement? Xenon 5d1 6s2. This is lanthanum. After this, we are adding 7 electrons, right? That's when the atomic number is 64. Means what we expect, it will be 5f7 because, sorry, 4f7. We are adding 4 electrons to the f. 5d1 6s2. Remember we said the mnemonic Segal. So cerium, gadolinium, and lutetium. These are the elements that will still have the electron in the d. First we will write it as it is, and then we will look at in which case the d electron will be shifted to f, and in which case it will not be shifted. In case of cerium and gadolinium and then lutetium, the 5d electron will not be shifted. Means what is the arrangement? It is 4f7, xenon 4f7, 5d1 6s2. So what is the correct answer for this? It is option B. Next we have a question that has come in the year 2015. So this question in a way summarizes most of the reactions of the potassium permanganate, acidified potassium permanganate. Assuming complete ionization, same moles of which of the following compounds will require least amount of acidified KMnO4 for complete oxidation? So which of them will require least amount of KMnO4? That's the question. Okay. Now there are different ways of solving this question. Of course, one way is actually knowing what are these reactions. So if you know the reactions, means we will be able to find out what is the amount of the KMnO4 required. So if you look at all these reactions are happening in where? Acidic medium. So if you look at the reaction of the FeSO3 ferrous sulphite with acidified KMnO4, this is the balanced equation. Okay, so 10 moles of FeSO3 requires what? 6 moles of KMnO4. Means 1 mole of the FeSO3 requires 0.6 KMnO4. Then the second is the FeSO4 ferrous sulphate. 10 moles of FeSO4 requires 2 moles of KMnO4. Means 1 mole of FeSO4, right? It requires how much? 0.2 mole of KMnO4. We are looking for which of them will be requiring the least amount of KMnO4. Next we look at ferrous oxalate, FeC2O4. What is C2O4? Oxalate ion. Then here 10 moles will require 6 moles. Means 1 mole of the ferrous oxalate requires again 0.6 mole of KMnO4. This is as per the balanced equations. The last is nitrite, ferrous nitrite. Okay, FeNO2 twice. So 2 moles of this is requiring 2 moles of KMnO4. Means 1 mole of this FeNO2 twice will exactly require 1 mole of KMnO4. Means in which case, if we take equal amounts of all these substances, right? So we are taking 1 mole, all the substance we are taking 1 mole. In which case we are requiring least amount of KMnO4? It is in the case of FeSO4. In case of FeSO4, we are requiring least amount of KMnO4, and this we can only answer this question if we are aware of the equations. So in a way it's a challenging question because it does require us to first know the equation and then also balance it. Then only we will be able to solve this. There is another method that we can use, and that method is in terms of what is the change in oxidation number. Like say for example, if you look at these substances, right, like we look at the ferrous sulphite. Ferrous sulphite, what is there? Fe is there in 2 plus, and SO3 2 minus means the sulfur is in the plus 4 state. So iron is in the plus 2 state and sulfur is in the plus 4 state. They are saying complete oxidation means iron will go to plus 3, here change is 1, and sulfur atom will go to what? Plus 6, means change is 2. So total change is what? The change in oxidation state is what? Totally iron will go to plus 3 means change is 1, sulfur will go to plus 6 means change is 2. Total change is what? 3. In case of FeSO4, right, in case of FeSO4, this is in case of what? FeSO3. In case of FeSO4, the iron only will undergo a change because sulfur is already in plus 6, oxygen is already in minus 2. So the Fe will undergo change from plus 2 to plus 3, means here delta is equal to what? 1. Then what we are having? FeNO2 twice. In NO2 twice, so this is NO2 minus. In NO2 minus, nitrogen is in which state? Nitrogen is in the plus 3 state. In NO3 minus, because it can get oxidized up to what? The NO2, nitrogen can get oxidized up to NO3. So in NO3 minus, nitrogen is in the plus 5 state. Nitrogen is in the plus 5 state. Means if FeNO2 twice, because here we don't have one, we have 2 NO2 entities. Means in this case, right, FeNO2 twice, the total delta will be, iron will undergo change from plus 2 to plus 3, means 1 will come. Each nitrogen, right, undergoing a change from plus 3 to plus 5 means 2 is the change. There are how many nitrogens? 2 nitrogens are there, means 2 into 2 will be what? 4. So totally delta will be equal to what? 5. In the case of FeC2O4, okay, so the delta will be, for the iron delta is 1 because it will undergo oxidation from plus 2 to plus 3. In this, right, C2O4 2 minus, right, the carbon oxidation state is plus 3. If it is undergoing complete oxidation means it will form what? CO2, where the oxidation state of carbon is plus 4. Means each carbon will undergo a change of 1 from plus 3 to plus 4. How many carbons are there? 2 carbons are there. So totally delta is equal to what? 3. In whichever case the delta is least, in which case the delta is least? In case of FeSO4, the delta is least. Okay, and that is going to be consuming lesser amount or lesser number of moles of KMnO4. So we can answer the question by actually knowing the balanced equations. Otherwise, we can also answer the question by looking at the given entity, right? When it is undergoing complete oxidation means iron will change from plus 2 to plus 3. Sulfur in FeSO3 means it will change. FeSO4 means sulfur cannot change. Already sulfur is in the highest oxidation state. In C2O4 2 minus, carbon can change from plus 3 to plus 4 when carbon is undergoing oxidation to CO2. Here also in this nitrite, nitrogen is what? Plus 3 state. It can undergo oxidation up to plus 5 state. So we will look at what is the change in oxidation state, and wherever the change in oxidation state is least, the corresponding amount of MnO4, because the MnO4 should balance this change, right? MnO4 should balance the change in oxidation. If one substance is having oxidation means other side there will be what? Reduction. So the balancing of this change is done by what? MnO4 minus ions. So wherever the change is least, that means in that particular case we will be requiring lesser amount of KMnO4. Let's move on to the next question. This is a question that has come in the cancelled paper of 2015, and this is based on again magnetic moment. We have seen in the first part video also some questions based on the magnetic moment. The magnetic moment 2.84 Bohr magneton is given by, so they are giving us 4 ions. We have to conclude which of them will be having magnetic moment of 2.84 Bohr magneton. See, first of all, what is the formula for the magnetic moment? Root of n into n plus 2. Squaring on both sides, right? 2.84 the square is equal to what? N into n plus 2. 2.84 the square means what? Approximately it will be 8. 8 is equal to n into n plus 2 means here n value will be close to equal to what? 1. N value will be close to equal to what? 1. Means we must have 2 unpaired electrons. We must be having what? 2 unpaired electrons. Now chromium, normally chromium, what is the structure? 3d5 4s1. Chromium 2 plus means what? First the s electrons will be removed. So chromium 2 plus means what? 3d4. 3d4, because of the way we arrange the electrons, right? How do we arrange them? In the d orbitals, first we will keep filling them with one electron having parallel spin. After filling all the 5 orbitals, then we will start pairing them, but 4 only are there, right? Means we will fill them with unpaired electron each. So the number of unpaired electrons is what? 4, not matching. Cobalt 2 plus. What is cobalt? Cobalt comes after iron. So cobalt is 3d7 4s2. That is the cobalt. Cobalt 2 plus means what? 2 electrons are removed. So 3d7. 3d7 means, if you look at this, right, how we are going to arrange? So first we will keep all 5 electrons into 5 orbitals, then 2 are filled. So the number of unpaired electrons is what? 3. So this is also not matching because we are looking for 2 unpaired electrons. Nickel 2 plus. Nickel is what? 3d8 4s2. That is nickel. After removing 2 electrons, it is 3d8. 3d8 means how we are going to arrange? First we will fill 1 electron each, 5 electrons are over, then the remaining 3 electrons we will pair. So the number of unpaired electrons in this case is what? 2. So 2 is the number of unpaired electrons. So nickel is the one that is matching our requirement because we are requiring how much? 2 unpaired electrons. So the correct answer for this is option C, which is nickel 2 plus. And we can check the other one also, titanium. So titanium is what? 3d2 4s2, titanium. Scandium is 3d1 4s2, right? So in titanium 3 plus means what? After removing 3 electrons, we will be having 3d1, means that is having 1 unpaired electron. That is also not matching our requirement because as per the given magnetic moment, what is the number of unpaired electrons we will require? We will require 2 unpaired electrons. That is coming only from the nickel 2 plus. Next, another question that has come from the same NEET 2015 cancelled paper. Which of the following processes does not involve oxidation of iron? So what are the processes that they are talking about? Formation of FeCO5, iron pentacarbonyl from Fe. See, CO is a neutral ligand. CO is what? It's a neutral ligand. And the iron oxidation state, normally iron, what is it? In the metallic state, iron oxidation state is 0. In FeCO5 also, the iron oxidation state is what? 0. Means iron is not undergoing any oxidation. So the correct answer for this is option A itself. In fact, we have complexes of the carbonyl group, like even nickel tetracarbonyl. This we will have in the vapor phase refining also. We will talk about it. The vapor phase refining method for the refining of nickel. So we will form the vapors of nickel tetracarbonyl. Here also, what is the oxidation state of nickel? It will be 0. Whereas if you look at the other options, right, liberation of H2 from steam at high temperature. So when H2 is released, basically it is because of the formation of the iron oxide. So iron is undergoing oxidation. Rusting of sheets, it's basically hydrated iron oxide. That is the chemical composition of the rust. Then decolorization of blue copper sulphate solution. So what happens when we have decolorization of blue copper sulphate? This is blue in color. So the iron sulphate is formed and copper will be deposited. That is the reason. So what is happening here? Again, iron is undergoing oxidation. The only case where iron is not undergoing oxidation is formation of the tetracarbonyl complex. Next we have another question that has come in the 2015 cancelled paper. Because of the lanthanide contraction, which of the following pairs of elements have nearly same atomic radii? Means as per the lanthanide contraction, which of the elements will have the same atomic radius? Now if you look at these elements, right, so where they actually belong to, zirconium and hafnium. These two, so zirconium is in the 5th period, hafnium comes in the 6th period. So while we are moving from zirconium to hafnium, zirconium atomic number is 40, hafnium atomic number 72. We are moving down the group. So we expect that the atomic radius will be what? Increasing. But as you move through the atomic number 40 to atomic number 72, we are going through the lanthanoids. We can see lanthanoids are going to come in where? They are going to come in the 6th period, right? After lanthanum they will be coming. So the lanthanide contraction, because of the inefficient shielding of the F subshell electrons, the size change will be compensated for. Generally when we add orbit, we expect that the size is going to be increasing. That is the explanation we have why the atomic size increases as we go from one period to another period. Because if you go in a group, right, generally what we say, going down the group, the size will be increasing because we are adding more and more number of shells. But when we move from zirconium to hafnium, right, we are moving through this lanthanide series. And because of the lanthanide contraction, right, one of the visible things that we will be able to notice is zirconium and hafnium, they will be having almost similar radius. So what are the elements that will have almost similar radius because of lanthanide contraction? It is zirconium and hafnium. Next we have a question that has come in the 2014. The reaction of aqueous KMnO4. This is another question based on the KMnO4 reactions. The reaction of aqueous KMnO4 with H2O2 in the acidic conditions gives. So if you look at the reaction of aqueous KMnO4 in the acidic conditions, it will be able to give us the potassium sulphate, manganese sulphate, water and oxygen. Means what we are able to see is that the H2O2 is undergoing oxidation. H2O2 is undergoing what? Oxidation. So what is happening? In peroxide, right, the oxidation state of oxygen is what? -1. Whereas in H2O, what is the oxidation state of oxygen? -2. In O2, what is the oxidation state of oxygen? 0. So it is undergoing a change from -1 to 0. Means what? It is seeing an increase in the oxidation state of oxygen. So we will say this reaction is example of what? The oxidation of H2O2 by KMnO4. So we can see what are the species that are getting formed if you look at in terms of the ions. Both if you take out these ions and write it in the ionic form, right, what we will be having? MnO4 minus ions plus H2O2 gives rise to what? Mn2 plus ions, H2O and O2. So what is the answer for this? Correct answer is what? Mn2 plus ions and then O2. So this reaction is example of what? Oxidation of hydrogen peroxide by the permanganate ions. So we have been seeing throughout that the questions on reactions of K2Cr2O7 and KMnO4, these are quite common in the NEET examination. Next we have a pretty straightforward question. This has come in the 2014. The reason for the lanthanide contraction is, so what is the reason for the lanthanide contraction? The poor shielding effect of the 4f orbitals. As a result of the poor shielding effect, so f orbitals are what? They are more diffused in shape. The f orbitals are what? Generally more diffused in shape. As a result of the poor shielding effect, right, the outer electrons, they will come under stronger influence of the nucleus. The poor shielding effect. So we are filling electrons where? Into 4f, pre-penultimate, because we are in the 6th period, right? Lanthanoids will come in the 6th period. Already 6s2 is there, and 5d1, we are filling electrons into 4f, means pre-penultimate. Where the electrons are filled, they are filled into pre-penultimate F subshell. So this poor shielding effect, right, will make sure that the outer electrons are under the stronger, they are coming under the stronger influence of the nucleus, because as the atomic number is increasing, the nuclear power will be also what increasing. But the poor shielding effect will result in outer electrons coming under more influence of the nucleus. So the correct answer for this is what? The lanthanide contraction is because of negligible screening effect of the F orbitals, and that is because of the diffused shape of the F subshell. Next we have a question that has come in the NEET paper 2013. Which of the following statements about the interstitial compounds is incorrect? So what are these interstitial compounds? First of all, the transition metals typically, right, they will be able to adjust the elements like small elements like hydrogen, carbon, nitrogen by trapping them in the interstitial void spaces. Transition metal crystals, they will have the interstitial voids. We talk about the types of voids in the solid state, the octahedral voids, tetrahedral voids, etc. The voids will be able to accommodate these small size atoms, typically the hydrogen, carbon, nitrogen. As a result of it, right, we will be forming the interstitial compounds. They will not usually have a particular stoichiometric formula, like we can have this is what TiC, this is what titanium carbon, whereas if you see TiH 1.73, so we are not having a specific stoichiometric formula because of the total number of void spaces being filled, etc. The composition or the stoichiometry will vary. The thing about these interstitial compounds is, as a result of it, right, the hardness of these materials will be increasing, because there are going to be now more interactions between, because the voids are filled. If you have two metal atoms, right, the void is now filled with element like carbon, nitrogen, etc. So there will be more strong interactions, or substances, they will become hard. They will be in fact harder than the pure metals, and because of the extra interactions, right, they will even be having higher melting points, slightly higher melting points, and of course they will be able to retain the metallic conductivity. The metal atoms, when they release the electrons out, these electrons will still be available for the conduction. But since there are already some existing chemical interactions that are coming into picture, right, these interstitial compounds, they will be chemically less reactive. So when we say that the interstitial compounds are chemically reactive, this is actually a wrong statement. So if you look at the question, right, what are we looking for? Which of the statements is incorrect or wrong? What are we looking for? We are looking for the incorrect statement or the wrong statement. So because of these chemical interactions that are coming into picture, right, because of these chemical interactions, the reactivity of the interstitial compounds will be lesser than the normal metals. So when we say that they are chemically reactive, means this is incorrect one. So which of them is incorrect? Option D is incorrect. They will have more hardness, they will have a higher melting point also, they will even be able to retain the metallic conductivity, but the chemical nature will be what? Reduced. The chemical reactivity part will be reduced. This is about the interstitial compounds. So this is what we have to cover in the part 2 video, and we will see in the part 3.